Okay, a few lectures back, I asked you for, as an exercise for homework, to have a go at the derivation at the bottom of page 24 in your lecture notes, where I asked you to try and derive the momentum conservation equations in the context of an arbitrary control volume fixed in space, so the Eulerian approach to deriving the equations. Which required you to use the vector calculus notation that we looked at previously for the continuity equation. So I thought I'd just do an example of how you might have gone about that. I think as a starting point I'd ask you just to think about some arbitrary control volume of any shape in 3 dimensions, and to define unit normals to the surface, so a field of normal vectors pointing out to the surface of unit length. We'll call this control volume V, and it's bound by surface S. And as a starting point I said to you that momentum conservation within that control volume implies this, that the surface integral, so the integral across the entire surface S of the momentum flux, and the momentum flux is basically our mass flux multiplied by velocity. So this term here is exactly as it was when we derived this for conservation of mass, but you've got an additional V term in here to make it momentum. So that's the integral of the momentum flux across the surface. And this will be positive for momentum flux out of the surface, plus the rate of change of momentum within that volume, so the time rate of change, d by dt, across the entire volume, so a volume integral now. Given that term, and that must be equal to the total force acting on the control volume. That's principle of conservation of momentum, essentially. So I've given you that as a starting point and asked you to use some of the principles that we did together for the mass conservation equation. For example, applying Gauss theorem to convert that surface integral into a volume integral and so on. The first step is to think about where this force term on the right hand side originates from in the context of the Euler equations. So the Euler equations don't consider viscosity, and as we mentioned, the norm is to ignore body forces, so and usually what we're talking about there is gravity. So we're ignoring gravity, we're ignoring viscous forces. So the only thing that can be driving this total force acting on this control volume is pressure, or the pressure gradient to be more specific. So actually we can write this term here as, as the volume integral, because we want to sum up the total force across the entire volume, of minus grad P dV. Now if you're not convinced about where that term comes from, or why it's possible to write that force vector term here in terms of the gradient operator acting on the pressure field, and it's the negative of that, and it's the negative of it because a positive force acts in the direction of negative pressure gradient, then what you can do is just remembering the definition for this del term, or the definition of this operator here in Cartesian coordinates. If you remember, I said you can consider this to be d by dx acting in the x direction, plus d by dy acting in the j direction, plus d by dz acting in the k direction. And then if you multiply that out, and just think about it in one direction, think about what this implies just in the x direction or just in the y direction. And hopefully you can see that the total force vector that you would get is actually given by this term. The next step then will be to convert the surface integral in the first term in that top equation. So we're going to convert this surface integral into a volume integral by applying Gauss theorem. So Gauss theorem, or often known as divergence theorem. And again, we looked at this and where this comes from in the lecture the other day. So applying Gauss theorem to that integral on the left-hand side, we can rewrite it as a volume integral. As plus d by dt, and it's possible to bring the d by dt inside the integral in this second term. So d by dt of rho v dv is equal to, and now on the right hand side of the equation we've got the volume integral minus the volume integral of grad p dv. So we've got volume integrals over our control volume across each of those three terms. So actually what we can do now, just as we did when we derived the continuity equation in this form, is take all of those terms over onto the left hand side and wrap them inside a single volume integral. So we can rewrite this as the volume integral of, and I'm going to rearrange the terms to put them in the conventional order that we write this out in, d rho v by dt plus and again we've got to think about what order here we would do this operation in. So this rho vector v is a vector, so this term here is a vector, and you can't take the gradient of a vector, so we must do this operation first. So our brackets actually should sit here. We're going to bring that grad p term over, and it's going to become positive on the left hand side. That's grad p dv equals 0. So there it is, we've got the integral form of the momentum conservation equations. It's actually, once you're comfortable with the terminology of vector calculus, it's actually much more straightforward to derive them in this form than it is in expanded Cartesian coordinates as we did in the lecture.